Okay, hello, Discrete Math. It is Wednesday morning, day 2 of our asynchronous learning. So, last week on Friday, we wrapped up the old unit and then we did a very brief 15-20 minutes max, maybe less, on basic counting principles. And actually, it was more or less just a review of some things that you learned in pre-calculus, or perhaps things you already learned doing math competition problems in middle school or whatever. But hopefully, we introduced a little bit more precision to the discussion. The only way to do counting problems is practice, and I'll say that. I think now maybe finally we're getting to the topic that you might have thought this whole class was about. When you signed up for Discrete Math, you were probably thinking, oh, isn't it like all that counting stuff? Yes, it is all that counting stuff. And ultimately, we're just doing a bunch of problems now. So if you are already very, very good at math team problems, then you're going to find all the things we do in this class are pretty easy. And especially this first homework assignment was pretty easy. And it's going to get harder, but still maybe, not so hard. Because these counting problems, they just get harder and harder and harder and harder forever. And the way you get really good at them is just practice. So much practice. And so once again, I will say, not to be intimidated if you see that there are other people in the class who are just immediately getting all of these problems right without even thinking about it. That's just because they are extremely experienced. And the only way to catch up with them is to just do a lot of counting. So this was our first homework assignment. And actually, just doing it right now, it was pretty easy, I think. Still, though, let's make sure that we all 100% get it, so that we can have a nice base to then push on to more difficult problems. Okay. I assigned this. I did this assignment. If we were at Blair in a normal year, then we would go over every single one of these problems and make sure that everyone got them all right. And actually, that would be probably like a waste of time for 75% of the class because these are maybe not so hard if you are experienced, and it would be helpful to some small portion of the class. The most helpful thing is actually to talk things out and to hear kind of diverse perspectives and different people's interpretations of the problems, and to hear where people went wrong and to kind of isolate their reasoning and to see where they may have been led astray. So unfortunately, we can barely do that during Zoom school, but we definitely can't do that on a video. So what's going to be missing from this video is hearing your contributions from different people, because oftentimes it is helpful to solve the same problem in 3 or 4 different ways. And also what we'll be missing are the parts where someone raises their hand and says, wait, why isn't it just this? And then we break down everything they said, and then we forgot, but no, that's not right. Okay, well, sorry. That's what we would have done if we were at Blair. And then the very next thing we're going to do after this is just more counting problems, which are significantly, I think, more difficult, but require no sort of new amount of background knowledge, just more experience. And what I would do on this day, if this were like a block class at Blair, I would go over all these problems, and then I would just let you work in groups to keep solving the more difficult problems. So for Zoom school, unclear exactly what to do about that, except try to kind of fake it through. And then on a video, this is just maybe not going to work at all. Well, point is that we hit an awkward spot in the class, and so I don't really have anything new to teach you yet. So here we are on this weird half week where we have asynchronous learning that was supposed to be going on Tuesday and Wednesday. So here it is Wednesday morning. I got to do something, so here's the plan. Now that I've finished rambling, I am going to go over this entire homework assignment. I think this is going to take like 15 minutes only to do all these problems, but of course it will probably take me like 30. Then you will watch this video, perhaps on 2 times speed, and then you will do more hard problems, which you have all day today to do, and I guess Thursday also, and even, Friday during lunch or whatever. And then on Friday, which is a half day, we're going to go over as much as we can the Friday homework problems, which I think are significantly more difficult and actually will involve us solving the same problem in sort of many, many different ways. So, okay, because these are easy, maybe there is only kind of like one way to do these. So this is supposed to be fun, but okay, here's a video. This is my first ever attempt to do like a screen capture, which I put off doing all first semester. And I'm also using this Google Jamboard. Sorry, Kevin, but I'm not using your buggy software right now. I'm just going to use the Google because they're so good. Without further ado, I have meticulously, because I'm a high-quality person, cropped, cut, and pasted from the PDF of our textbook all of the homework problems, and then we're just going to go through them really quickly, and I hope I don't do anything wrong. Okay, let's go. Tomorrow night I plan to listen to one of 12 cassette tapes, and then eat one of 4 frozen dinners. Cassette tapes. Gossett, you're so cute. This textbook's like 15 years old, but even then I think he was being intentionally like, old about this. I had cassette tapes when I was a kid. They're great. Well, look, man. After dinner, I will put together one of 3 picture puzzles. I don't even know what that means. I guess that's a jigsaw puzzle or something. How long can I maintain such an active schedule? I guess this is like ironic or something. So, how many different ways can you do such an exciting evening? I guess this is like dry humor or something. Well, let's go. We have 12 cassette tapes, so I have 12 choices. Look at that. For which cassette tape to listen to. And here comes the multiplicative principle. For each one of those choices of which cassette tape to listen to, I have 4 choices for which frozen dinner to eat. So that's why I multiply by 12, because it really is, you should think of it as, for every cassette tape, there are 4 choices for which frozen dinner to eat. And then for each of those choices, combined choices of cassette tape and frozen dinner, there are 3 choices for which picture puzzle to put together. And so the answer is 12 times 4 times 3. That's the multiplicative principle. That's 144. Okay, that's like a 3rd grade math team problem. Next page. Woo! Look at this professional. This is great. Okay, a boy needs to eat breakfast and lunch, practice piano, mow the lawn, and read a book today. In how many ways can he arrange these activities, assuming he doesn't care in which order the meals occur? Okay, so built into this question, assuming he doesn't care in which order the meals occur, this implies a certain interpretation of breakfast and lunch. And actually, one benefit of having this conversation live in class or watching this video is to just hear all the various interpretations of all the various problems. So this is like my impression of Mr. Stein's class, where you guys do statistics problems and you spend half the class basically just talking about Stein's psychological interpretation of the hidden assumptions of the problem and discussing how to solve the problem in 4 different ways depending on how you interpret the ambiguity in the problem. So we're going to do some of that today. But here I don't think there's much ambiguity, because if he doesn't care in which order the meals occur, that implies that you can eat lunch before breakfast. That implies a definition of breakfast based on not the order in which the meal occurs, but based on the content of the meal. So some people would say if you just like wake up at 7 a.m. and have like a hamburger, then that's breakfast. And be like, ooh, why are you having a hamburger for breakfast? No. Gossett, it seems to be interpreting breakfast as like, pancakes and like eggs and stuff. That's like what you get when you go to a diner and they advertise like breakfast all day. That's what they're talking about. So therefore breakfast, so you can have lunch before breakfast basically. All right, well in that case there's just freaking 5 activities, man. There's breakfast, there's lunch, there's practicing piano, there's a mowing the lawn, and there's a reading a book. And then I just have these 5 activities. How many ways can I arrange these activities? Well, this is just how many ways can I permute these 5 letters, basically. So, okay, answer 5 factorial, because 5 choices for what to do first, 4 choices for what to do second, etc. All right, woo, that was exciting. How many tours consisting of a visit in the order specified to a park, a museum, a mall, and a restaurant are possible if we can select from 5 parks, 2 museums, 6 malls, and 8 restaurants. Okay, well, in the order specified means I'm going to first go to a park. How many parks are there? 5. So I have 5 choices for what park to go to. Then there are 2 museums, so I have 2 choices for a museum to go to. Then I have 6 malls, and there are therefore 6 choices for which mall to go to. And 8 restaurants, and therefore 8 choices for a restaurant to go to. And once again, the multiplicative principle says that for every choice of there are 5 choices for which park to go to. For every one of those choices, there are 2 museums to choose from. And for every one of those park-museum combinations, there are then 6 restaurants that are possible. And for every one of those, okay, so it's the multiplicative principle. Ideally, if you want to think absolutely clearly, especially when the problems get more difficult, you should constantly, every time you use multiplication, don't do it lazily. Use multiplication with sort of like meaning and purpose. Every time you apply every time you go to do multiplication, just ask yourself for a half of a second: is the multiplicative principle here applicable? Is it true that for every one of these there are this many of these? And in this case, it's clearly true. Okay, woo. Number 6, suppose that either a doctor or a dentist is chosen to speak about his or her profession to a 7th grade classroom. How many choices are there for the speaker if there are 70 doctors and 23 dentists available? Okay, this is just a silly problem. We need to pick a doctor or a dentist. Well, there's 70 doctors and 23 dentists, so there are clearly 93 choices. This is Gossett's attempt to write a problem to illustrate the other multiplicative principle, the additive principle. And the additive principle says that if you want to count the total number of doctor-dentists, then you can partition this set into the doctors and the dentists. And I use now like the real meaning of partition, so in a way that you've that is exhaustive and non-overlapping. If the total number of things you're trying to count can be broken up into sort of 2 pieces, then if you count them individually, then you can just add them together. Okay, this is kind of stupid. 11. All of these are just so easy at first. Suppose that for a conference, individuals looking for a badge with 5 features, a color. All right, man, how many colors are there? There are 7 colors. For each choice of color, I get to also choose a shape. Ooh, there are 8 shapes. For each choice of color and shape, I need to choose an uppercase alphabet letter. This is presumably the English alphabet under discussion. So there are 26 of those. And then I get to choose an animal. And then I get to choose a 1-digit number. And there are, I guess there are 10 1-digit numbers if we're including 0 and stuff. I don't see why not. So there you go. It's whatever that is. All right. Are these getting any more difficult? A little bit. An individual won a raffle and can choose a prize from one of 4 lists. The first list contains 19 possible prizes, while the second, third, and fourth lists include 14, 21, and 18 items, respectively. How many prizes does the raffle winner have to choose from? This is just a silly problem. You just add them all up, man. So it's just 19 plus 14 plus 21 plus 18. Whatever that is, according to my paper, 72. I guess I could have just done the addition myself, but this seems easier. 37, yeah, that looks right. Good. Once again, it's the additive principle. If we want to know the total number of prizes, then we can partition that into a bunch of disjoint subsets. Well, here the problem already comes to you partitioned. Notice how I've chosen to put my beautiful little face here in the corner of the screen instead of just hearing my voice. So that is an interesting choice that I made. Woo! Next week, I intend to visit my old hometown. I wish to visit 5 friends, but have time to see only 3 of them. In how many ways can I schedule the visits? All right, this is starting to get exciting. We're getting to 5th grade math team problems now. Well, you have 3 time slots, and you have 5 friends. So, how many ways can I schedule the visits? Well, does it matter which friend you see first? I think it definitely matters, because friends are people, and people have like emotions, and people care about things. Plus, you want to schedule your trips in such a way that you can maximize your kind of gossip potential. Like, if you're only going to see 3 friends, you want to see one first, who you're not going to talk smack about the others with, And then you can see your second friend, you can gossip about the first one. Then when you see your third friend, you can gossip about the previous two. So also, some people are morning people, some people, et cetera, et cetera, et cetera. So, okay, point is, yeah, man, anytime people are involved, the order always matters because people matter. So the idea here is that I have 5 choices for who to visit first, for which of my 3 friends to visit first. Not to mention even things like, driving, maybe they live in far corners of the area. Okay, so then I have 4 choices for who to visit second and 3 choices for who to visit next. And okay, I don't think we need any more theory in this problem. There it is. Good. 20. Oh, this one's a little bit exciting. Suppose you're taking a bus trip from your home in Florida to California. Ooh, you live in Florida. Sorry. Let's go to California. Well, I'm going to make a graphic organizer here. There are 7 different bus services offering trips from Florida to Arizona. Why would we go to Arizona? Well, because if you're going to go cross-country via bus, then you can't be expecting, direct buses or whatever. I know someone who actually did this. They were so broke. They were like 24, and they had to get from, I believe, Chicago to L.A., and they took like just a Greyhound bus. It took like 4 days. It's a very interesting experience. You should do it once, maybe. Well, I didn't do it, but she did. 7 different routes are possible from Florida to Arizona. And wait, am I even reading this problem correctly? There's 7 different bus services offering trips from Florida to Arizona. 4 offering trips from Florida to Texas. So there are 4 different bus routes from Florida to Texas. 8 offering trips from Arizona to California, and 7 offering trips from Texas to California. How many possibilities are there for a bus ride from Florida to California via either Arizona or Texas? Ooh, this is a multi-step problem which involves both of the core counting principles. The idea here is that I can count the total, watch this, number of trips from Florida to California via Arizona, and the answer is that there are 56 of those because, there are 7 ways to get from Florida to Arizona, and for each of those 7 ways, there are then 8 choices for how to get to from Arizona to California. So that's the multiplicative principle in play. But then, how many choices are there to get from Florida to California via Texas? Answer 28, because there are 4 ways to get to Texas, and then for each of those 4 ways, there are then 7 ways to get to California from Texas. So you multiply, but now I use the additive principle to just add those up. So the answer to this problem is 84, because I've partitioned the ways of getting from Florida to California into the ways via Arizona and the ways via Texas. This is all just like really easy. Okay, 21. I'll be sharing an apartment with 2 friends. The apartment has 1 large and 1 small bedroom. 2 of us will share the large bedroom, and 1 will sleep in the smaller room. And how many distinguishable ways can we assign the rooms? Okay, well, this is a really easy problem because basically think like a human being for a moment. What's the first thing? Well, it's really nice to have your own room, I guess, unless you're like a 10-year-old and you like sleepovers. So if you want your own room, then, well, there are 3 choices for who gets to sleep in the small bedroom alone and get some kind of privacy. And once you've decided who sleeps alone, then the problem is over, because then the other 2 will just go into the large bedroom. So there are therefore just 3 ways to do this. Okay, the day after 9 students complete an exam, the teacher passes out their grades. The possible grades are blah, 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 blah. How many ways can the grades be assigned to the students? Kind of a little bit vague because, answer 1 way, fairly. But okay, what we really mean is sort of how many possible outcomes could there be? Well, the 9 students are all totally independent of each other, and each of the 9 students has 5 possible grades. So there are 5 grades that I could give to student 1, 5 grades I could give to student 2, etc. And so the answer is a whole bunch of 5. So this is just 5 to the 9th. This is some kind of, I don't even remember what he called this. Something with repetition. But anyway, it's just 5 to the 9th. So that's a thing. Okay, good. All right, this is a crazy problem. I actually maybe want to go back and do that one later. Should I do that? Go back? I think I will go back and do that one later. Let's do 25. 25. A recording artist plans to play 6 songs on her new CD. In how many ways can she order these songs? Okay, this is just a pretty obvious problem, I think. In how many ways can she order these songs? Well, if there's 6 songs and the order doesn't, and any order is possible, then there's just simply 6 factorial. Kind of by definition, at least that's how we did it in class, ways to do that. In how many ways can she order these songs if she has already chosen the first and last selections? Dude, if you've already chosen the first and last selections, then there are really only 4 songs left that you need to find the order of, so that's just 4 factorial. All right. 28. This is getting exciting. You have 10 fingers. True. Assuming that your fingers were made of rubber and it was possible to reach any combination of 10 keys simultaneously, how many 10 key combinations are there? Okay, so this is like piano, but unbound by, I don't actually play piano, so I don't know anything about this, but you're unbound by the physics of the length of your fingers, and so you can just kind of put out your little like tentacles and touch any 10 keys anywhere on the keyboard in any kind of order. But at the moment, note that we are not interested. I know that people who play piano, I guess, when you learn how to play piano, it's very important that you learn to do it the correct way, where you're like touching the correct key with the correct finger or whatever. There's like good and bad ways to do this, but never mind all that. How many 10 key combinations are there? This is going to ignore which of your 10 fingers is touching which key, but simply how many ways can 10 of your fingers be made to touch 10 keys? Well, okay, this is exactly what this notation, this combination notation was invented for. And so the answer to this problem is 88 choose 10. What is 88 choose 10? It is, by definition, the number of ways to choose 10 objects from a set of 88 objects. Here, the fact that 52 are white and 36 are black is just irrelevant, and I just want to touch 10 keys. So this, by definition, is the number of ways to choose 10 from a set of 88. Okay, but suppose you, and this is probably what you wrote down, and this is probably you just stopped there and didn't do anything else, and that's actually what I would recommend. But let's remind ourselves, kind of what the actual formula for 88 choose 10 is and why. Because in this class we've taken it as the definition, so it's almost kind of sort of tautological or something to just leave it like that. Sorry, didn't mean to have that times there. So okay, what is 88 choose 10? Well, no, I didn't mean to have that times there because so that's my answer. Let me put a box around it. But what can I say about 88 choose 10? Well, it's the number of ways of choosing 10 keys from the set of the 88 keys. Now, suppose I do care about which fingers were touching which keys. So now I am going to introduce some sort of extra structure, and I'm going to say, okay, having now chosen the 10 keys, let me now decide if my fingers are really rubber, I can go and any one of my 10 fingers can touch any one of those 10 keys. So put a little sticker on those 10 keys or something and designate those 10 keys as the keys of interest. And now I'm going to decide sort of which finger touches which key. Well, putting your fingers in some kind of order, like 1, 2, 3, 4, 5, going from left to right or something, then any one of those is possible. So which key should my left pinky go to? Well, I have 10 choices. Which key should my left ring finger go to? Well, I have 9 choices. So there are 10 factorial, sort of obviously, ways to decide which of my 10 fingers go to which of the 10 keys. Now, if I multiply these two, the multiplicative principle suggests that if there are 88 choose 10 ways of choosing which 10 keys I'm going to play, For every one of those ways, there are 10 factorial ways to decide which finger touches which key. Therefore, there are the product of these two ways to decide which of my 10 fingers should touch which of the 88 keys on the keyboard. And this is, in fact, 88 P10. And then let's not stop there. What if I then say, okay, well now I have, if we're just doing fantasy, we might as well imagine that I have 78 other digits. Suppose I am some kind of, disgusting alien creature with 78, like, antenna or something. Or antennae, one of those two is the right word. And now I'm going to play, like, all the piano keys simultaneously with my 10 creepy, disgusting rubber fingers and my 78 antenna or antennae. Well, how many ways are there to do that? Well, of course, my antennae are all different, and each one is providing, slightly different sensory experience on my alien world. So it does matter which of my antenna touches which key. And so, in fact, I have 78 factorial ways to decide which antenna touches which key. And okay, if I now multiply all of these together, then what do I get? Well, now I might as well just say that I have 88 appendages and there are 88 keys, and I'm just deciding for every single appendage which key to touch. And so the answer is that this is 88 factorial. Okay, this is me sort of slowly going through. This is not maybe the ideal problem. This is me slowly going through the logic behind sort of everything that's going on here. If I now divide, then I get that there's this formula, 88 choose... I've now proved combinatorially, as they say, what the correct formula is for 88 choose 10. It's 88 factorial divided by 78 factorial times 10 factorial. Yes, I did this last class. Yes, I did this in Pre-Calc C, but now I'm doing it maybe, better or slowly or more carefully or something. I've proven to you this formula for calculating 88 choose 10. And the way we're going to do it in this class, 88 choose 10 is the answer to the problem sort of by definition. But if you want to know the relationship between 88 choose 10 and numbers, then this is the formula kind of for this symbol. And the reason is a combinatorial reason. Choose your 10 keys, then permute those 10 keys, then permute all the other keys. Then you have permuted all the keys. Okay, good. All right. Going faster now. A standard octave contains 12 keys representing distinct musical notes, triad chords, blah, 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 blah. Okay, so basically how many ways can I play 3 keys? Answer 12, choose 3. That's all I'll say there. There are 12 choose 3 ways of choosing from the 12 keys of your octave which 3 that we are going to play. Woo! This is exciting. Okay, here's Gossett again being just kind of cool, weird. I don't know. You decide. But he found some kind of business text or something. And the Mythical Man Month. I don't know what this is. This is probably some mid-century business work. If there are n workers on a project, there are n squared minus 2 over n interfaces across which there may be communication. And there are potentially almost 2 to the n teams within which coordination must occur. The purpose of organization is to reduce the amount of communication and coordination necessary. Hence, organization is a radical attack on the communication problems treated above. Okay, so this is perhaps an example of, I haven't read this book, I've never even heard of it, but, some people who are writing, pop business books or whatever will try to intimidate people with math or whatever. So Gossett's come on now, let's just make some sense of these wild claims or people are throwing numbers around. Is this true that there are n squared minus n over 2 interfaces across which there must be communication? What is this person talking about? I see. If there are n workers on a project and an interface is a one-to-one conversation, one-on-one conversation, then that's an interesting question. How many pairs of people are there? If there are n workers on a project, well, there are then n choose 2 possible pairs. n choose 2 is, by definition, for us, the number of ways of choosing 2 objects from a set of n objects. And so if we have n workers, then there are n choose 2 sort of pairs of workers. And what is n choose 2? Well, we have just seen that there is a formula for this, that it is n factorial over n minus 2 factorial to factorial. And this becomes just n, well, okay, you've all sort of seen this before, so I don't think I need to do this, but, you know, if you really want to, n factorial is n times n minus 1 times, and then, like, the rest of them, so that's n minus 2 factorial, but then there's also an n minus 2 factorial down here, and 2 is just 2 factorial, and so you get this cancellation, n minus 1 over 2 is, in fact, n choose 2, and that's where this number is coming from. Okay, so that is my mathematical justification. Provide a mathematical justification for the claim: if there are n workers on a project, there are potentially almost 2 to the n teams within which coordination must occur. Yeah, and note the use of this weird phrase, you know, almost, potentially almost. Okay, well, I guess it matters what's a team. So what is a team? Well, I guess it's just a group of people. So the question is, how many groups of people are there? If you have n people, how many groups are there? Well, we can sort of count all the groups of size 1. Perhaps you think that's a group. That's like, you know, kind of a group. All the groups of size 2, all the groups of size 3. This sounds really hard or something. Where does this 2 to the n come from? And in fact, that's maybe how, if you were, you know, not maybe thinking clearly about this problem, this is what you might have done. You might have said, all right, let's see, there are n choose 1 ways of picking a group of size 1. This is true, by the way. There are n choose 2 ways of picking a group of size 2. There are n choose 3 ways of picking a group of size 3, all the way up to there are n choose n ways of picking a group of size n. So that's picking all of the people or something like that. Yeah, that would be one way of making a team. Just put everyone on the team. And so you may have gotten this far and then said, like, what? Well, what am I supposed to do now? Why is this 2 to the n? Okay, well, we did this in Pre-Calc C, or you can just use your brain, a moment's reflection, or perhaps you didn't pursue this this way at all, which would have been better. Make a team. Go put your n employees in order, say alphabetically by last name. Now let's go make a team. Well, okay, let's go to the first person whose last name is, you know, Aardvark. And then we have to decide, should I include Aardvark on my team or not? I have 2 choices about whether or not to include Aardvark. Let's go to the second person on my team, last name Aardwolf. Should I or should I not include Aardwolf? 2 choices. Go to the next person on my team, you know, last name Beowulf. This is not even funny. So there are 2 choices. So for every single employee on the team, for every single employee in the company, I have 2 choices about whether or not to include them on a team. And so I have, in making an arbitrary team, I have 2 to the n choices to make. And having made every single one, every single different choice is going to result in a different team. And so if there are 2 to the n choices, then there are 2 to the n different teams. This is just summarizing a basic principle that I think you already know, which is that if you give me a set of size n, then there are 2 to the n subsets of that set. This is something even we did on the first week of school when we talked about set theory, right? That the size of the power set of A, I think this came up in this class, is just 2 to the size of that set for all the exact same reasons. And so a couple exciting things happened. One exciting thing that happened is that I have solved this problem, and that I know why the answer is 2 to the n now. What's up with this almost thing? Well, who can know what the writer of this business work meant, but perhaps almost could refer to the fact that if you put no people on your team, that's like not a team. So while it is true that there are 2 to the n subsets of a set, that includes the empty set, which is a subset of every set, but perhaps the empty set is not a team. So if you're talking about teams with an actual non-empty number of people on them, then there are in fact 2 to the n minus 1 teams. So that would be my answer to how many teams are there, and that's why this person is kind of saying almost. And that shows that if I want to write now a mathematically true formula, I need to include n choose 0. What is n choose 0? That's the number of ways of choosing no people. And if you choose no people, then you have an empty team. And there's one way to choose no people, and that's the choice consistent with the empty set. I might actually make you feel better about the fact that n choose 0 is 1. I gave that about 10 seconds of attention in class. But if we're really taking seriously that n choose 0 is to be defined combinatorially as the number of ways of choosing no objects, then you might find that to be a little bit controversial that I said that there's one way of choosing no objects. But if you think maybe perhaps more abstractly in terms of set theory, there is certainly, one set of size 0. And so the choice of no objects is consistent with the empty set, and so that might make you feel sort of more confident about that combinatorial argument. Anyway, the answer is if you add these all up together, this is 2 to the n. So this is a kind of a deep mathematical fact about counting, and we just did what's called a combinatorial proof. And this is going to be the big subject of next week. And this is the big thing we're going to do in this class that's different from what we do in Pre-Calc C. Besides the problems just being harder, we are going to reason kind of abstractly about counting. Or we're going to reason abstractly via these counting sort of arguments. I just gave an argument that these two are in fact the same. And okay, let's keep going. We did this in Pre-Calc C, but for like a second, and I didn't expect you to necessarily understand it. All right, man, we got to finish this up. A local pizza store offers a choice of 7 toppings and 3 sizes. How many distinct 3-topping pizzas do they offer? Well, am I doing this right? 31, 7 choice. Choice of 7 toppings and 3 sizes. Okay, I guess I have to. I guess there are 2 interpretations. Interpretation number 1 is that everyone wants as many toppings as possible. Usually you pay per topping. So it would be a pretty chaotic pizzeria. I worked at a pizzeria, by the way, for several years, and you certainly pay per topping. The toppings are so expensive. It turns out when you do the economic analysis, cheese and dough is really cheap. Man, dough is just like flour and water and a tiny bit of yeast. It's like borderline free. And sauce isn't too expensive either. Cheese is a little bit more so. Anyway, when you sell a plain pizza, just cheese, you make so much money, and it's amazing. But when you start selling some kind of like broccoli crap, or like we had chicken pizzas or mushrooms or any of that kind of stuff, suddenly your profit margins shrink dramatically because it takes a lot of labor to like prepare all that chicken. You got to bread it and grill it and cut it, and it's really annoying. And that stuff's really expensive too. Broccoli is like expensive. So point is, if you wanna make a lot of money, you should sell only plain at your pizzeria. Anyway, you pay by the topping for sure. So if there are a choice of 7 toppings, then that would be a pizzeria in which you were just allowed to choose whichever toppings you want, I guess. That's kind of crazy. What? I'm looking at my own answer and I don't even understand it. 3 times 7. Choice of 7 toppings and 3 sizes. How many distinct 3-topping pizzas do they offer? Perhaps I should read the freaking question. I guess this is not ambiguous because if you are definitely going to pay per topping, and now you're going to pay specifically for 3 toppings, so you're going to freaking get your 3 toppings. So you just have a choice of which toppings. And all right, so you're just gonna, if you're a normal person, you're gonna call up and just say, all right, for my 3 toppings, I would like, mushrooms, sausage, and onions or something like that. Well, then, from among the 7 toppings, there are 7 choose 3 ways of picking which 3 toppings from among the 7 toppings. And for every one of the ways of picking which toppings you want, there are then 3 choices for what size to get. And so I guess the answer to this problem is just that. And what is 7 choose 3? It's 7 times 6 times 5 over, you could just leave it like that, but the numbers are pretty small. 7 times 6 times 5 over 3 factorials, so that's like 35 times 3, so that's like 105 is my answer here. Is there even another possible interpretation? Basically not, unless you want to talk about some kind of weirdo who's like, look, I love mushrooms so much that for my 3 toppings, I want all 3 of them to be mushrooms. That would be, let's not talk about that guy. All right. This is, I think, the hardest problem from the whole homework. A Fletcher is making some arrows. Each arrow has 3 feathers on the tail end, spaced at 120-degree intervals around the shaft. Okay, so it's like this. You have, I can't draw, but you have like an arrow, right? And here's like the arrowhead or whatever, and that's like the sharp part. And then on the back, you have like a little zoop, 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 and this is gonna get all like spinny, spinny. So I don't know anything about, I guess I learned just from going over this homework problem that is like this word, Fletcher. It just means someone who makes arrows. And I suppose if it's like, 300 years ago or maybe 1,000 years ago or something, it's very important to like decorate your arrows with your particular colors. So like when you, on the battlefield later or something, you can see, who you killed or whatever. Or maybe let's take a more innocent interpretation. If you're doing arrow practice and everyone's shooting their arrows all over the place, then you want to go collect the arrows that you made. So if you put a lot of time and effort and money into making your arrows, you want them to be distinctive so that afterwards you can go out into the open field and everyone can know which arrows are theirs. So we decorate our arrows with various colors and we put them on the back, and then it looks pretty, as the arrow is kind of spinning round and round, it's very pretty looking. So suppose we have just 4 colors: red, blue, yellow, and green. And from these 4 colored feathers, I am going to choose what is going to be my distinctive personal pattern. And how many visual distinct patterns are there if a color can be used in more than one position on an arrow? Assume that rotating the arrow does not result in a different pattern, but changing colors does. I've just been, so when you shoot the arrow, perhaps it has some kind of spin to it. I guess that shouldn't really happen, but anyway, certainly if you picked up the arrow and you kind of spin it around, it's just the same arrow. So that's what we mean by that. Rotating the arrow does not result in a different pattern. Almost didn't need to be said. Of course not, because the arrow is completely symmetrical. So if you just pick up an arrow, right. Okay, so what I mean by that is, for example, suppose you had just like red, blue, and green or something. There's just obviously no difference between that and, red, blue, green. That's just the same arrow. You're just looking at it from a slightly different perspective or from a different angle or something like that. So we should not count these 2 twice. But, and this is subtle, the fact that it's an arrow is slightly relevant because there is like a kind of front and a back. And so when we say visually distinct patterns, we should imagine, the arrows flying through the sky or something, and you're looking at the arrow from behind. So I do think that there is a difference between, here, let's do it like this. There is a difference between this red, blue, and green arrow and this red, blue, and green, like that. These 2 are different. One may pick up an arrow and looking at it from the back, which is something you can do. Okay, this says around the shaft, but still, depending on whether it's over here or whether it's somewhere around here, it doesn't matter because there's certainly a front of the arrow. And if there's certainly a front of the arrow, then there can be such a thing as looking from the back. And therefore, these two really are different, right? If I had a red, a blue, and a green sort of going in that order clockwise, I guess what I'm trying to say is that clockwise makes sense because the arrows have fronts. This is just a different arrow. It's absolutely visually distinctive. If you pick up two arrows in which someone has chosen to put the red, blue, and green feathers in that order counterclockwise around the shaft, and a different person who's chosen to put the arrows in a counterclockwise order red, green, blue around the shaft, those are two totally different arrows. So we do need to count those separately. So that's kind of interesting, that bit of background information. How are we going to solve this problem? Well, there's like a very, very sophisticated way to solve this problem that I can't remember right now, and that requires some knowledge that we don't have yet. So let me just do it the boring and methodical but correct way. First of all, suppose you're the kind of person who's just like a solid color kind of person. Then you might want to just choose all red. You can do that, or all blue, or all yellow, or all green. Well then, without any further commentary, I claim that there are just 4 possible ways to do that. But now, suppose that you're going to do a 2-in-1 or something like that. Well, if you're going to do a 2-in-1, so in other words, you're going to do, say, 2 blues and a yellow, say. Well, then I claim that now there are not different ways of doing 2 blues and a yellow. In other words, if you try, following my logic over here, to draw these in, to sort of care about the orientation, you quickly find that, like, yeah, if you just put the blue, blue, yellow here, or I guess, let's see, if I'm doing this in the most respectable way, I should say blue, like I did before, but now try to go, like, in the other direction. So now, instead of the next one being a blue, the next one, quote-unquote, counterclockwise would be yellow, and then the next one blue. But I hope you're sort of seeing that these are, in fact, just the same, right? So I can't tell the difference between a blue, blue, yellow arrow and a blue, yellow, blue arrow. Because if you just spin it one more time, then that's just the same arrow. Okay, and there's actually something deep going on here, but maybe I won't say it at the moment. The point is that I don't need to care about, I don't notice this sort of clockwise, counterclockwise thing when I have only a 2-in-1 situation with just 3 feathers. Therefore, when it comes to counting how many 2-in-1s there are, all that matters is of which color is there 2 and of which color is there 1. Okay, so the answer is I have 4 choices for which color to be present twice, and I have 3 choices for which color to be present once, if I am deciding to have a 2-in-1 pattern. And so therefore there are 12 of those. And then there's the, like, you know, all different or whatever option. And for the all different option, well, now I have to choose of my 4 colors, you know, which 3 of them should go on my arrow. Well, now using something called complementary counting / common sense, if I need to choose which 3 colors from my 4 colors to pick, that's just equivalent to picking which color I don't like and taking all the rest. So I claim that there are sort of obviously 4 different ways of picking which 3 colors out of the 4 should go on my arrow, assuming I'm picking 3 different colors. I guess the answer is just 4 choose 3, but 4 choose 3 is also just 4 factorial over 3 factorial, 1 factorial, so that is just 4. So that's like a kind of a check on that logic. Okay, but now comes the subtlety, which you may have missed, which is that I have to multiply by 2. Because even after having decided which 3 colors to use, there are 2 sort of clockwise, counterclockwise orders to go in. And so there are 8 of these. And now, using the multiplicative principle that I have partitioned all the possible ways into ones in which they are the same, 2-in-1, and all different, I now add, and the final answer to this problem is 24. All right, it is very fascinating to hear how you solved this problem, because I think there are other ways. And It's very fascinating to hear all the ways you tried to solve this problem and got it wrong, and why those ways are wrong, but oh well, Zoom school. Okay, going on to the next problem. This is actually, in some ways, it would have made more logical sense to do this problem first, because this is more of a principled analysis of this kind of rotation sort of thing. So, how many ways are there to situate 4 people in identical chairs at a circular table? Okay, well, this is maybe a little bit controversial, because if there are 4 identical chairs, so it's not true that one of the chairs is like fancy or something, then it shouldn't matter sort of in which chair you're in. So what are we even talking about then? Well, if we are situating 4 people, anytime people are involved, even without the author of the problem explicitly saying so, we sort of care who people are. We recognize people and we care about their personalities and stuff like that. So it does matter who is sitting sort of next to you at the table, who you can talk to. And in particular, if you're at a 4-person table, then, it's hard to maybe like gossip with the person all the way across the table, say, or some kind of, who knows, footsie or whatever. So what's really happening here is what the author of this problem, Gossett, is trying to say is, how many ways are there to fit 4 people around a table in which the only thing that matters is the relative positions of a person to the people around them? And also it matters who's on your left and who's on your right, because perhaps you're deaf in your left ear or something like that, and so you're going to have a hard time gossiping with the person to your left. Or perhaps you are, I don't know, man. There are just reasons why it should matter who's to your left and who's to your right. Perhaps it's a poker game, and so betting is going around the table in a clockwise way. And so it certainly matters. The person to the left of you will then always be bidding just before you, and the person to your right will be bidding just after you. So that's a thing. Okay, also built into this problem is that, all right, sure, the chairs are identical, but if we really don't care, usually if you're in like a normal room, then there might be a better view, from one position or another around the table. So if you're going with 4 people to a restaurant and you're going to sit around a circular table, then usually you sort of do have a preference for one seat or the other, because it's like near the bathroom or it's far away from the bathroom or whatever, drafty position you have near the front of the restaurant or something. But okay, we need to ignore all that. So if you want to go full in, you can imagine that the table itself is even just sort of rotating. And so not only are the chairs identical, but even the table is sort of continuously rotating at a very, very slow rate. And so it really, really doesn't matter your position at the table in any kind of absolute sense. That's what this problem really wants you to think about, right? The absolute position on the table is irrelevant. All that matters is the relative position at the table. Okay, so this is the kind of a classic problem that you solved in middle school or something like that. And the answer is, well, here's one possible solution. There are 4 factorial ways to place the 4 people at the 4 spots at the table. But then that overcounts, because in fact, if you rotate the table, then that's the same table or something like that. So some people think of it like this. It's 4 factorial divided by 4. Why are we dividing by 4? We're dividing by 4 because there are 4 rotations of a 4-person table, and for any one way of assigning people to the tables, you've overcounted by a factor of 4, because each of these 4 rotations will produce a sort of a different table according to your new count. But those are in fact all the same. I find that kind of awkward. Another approach is to say, like, well, if the relative positions really don't matter, then let's let the person whose like feet hurt the most, sit down first. And so if person A just sits down at sort of an arbitrary spot, well, now the question really just becomes how many ways are there for the 3 remaining people to fill up the 3 remaining spots. And I feel that it is fully arbitrary where A sits, because if this table is rotating all around, then there's absolutely nothing to distinguish any one spot at this table from any other spot. And so we might as well just let person A sit down first. But now that person A has sat down, it does matter. Every other spot does matter. For example, only one person can be to person A's left. And so there are 3 choices for who goes to the left of person A. Then there are 2 choices for who goes opposite person A, and then there's only 1 choice for who goes to the right of person A. And so you can sort of solve this problem more directly as just 3 factorial. And sort of by seating one person, you sort of unwrap the table, so to speak, and now there kind of is a linear order, and the linear order is like, you know, who goes, I guess if we're unwrapping it sort of this way to make it like flat or something, then it should be who's going to go here in the 1 position to the right of person A, and then in the 2 position and in the 3 position, and then it's sort of more clear that the answer is 3 factorial. Okay, so sort of more generally then, this is what's called a circular permutation. Circular permutation. If you have n people sitting around a circular table in which there is no nothing distinguishing a position from any other position except who they are sitting relative to, then there are going to be n minus 1 factorial ways to do this. And I think the clearest way is to kind of do what I said, right? So you have a certain, let the first person just sort of sit down at one spot, and now you've turned the circular permutation problem into a linear permutation problem. And there are n minus 1 factorial ways for the n minus 1 remaining people to sit in those n minus 1 remaining spots. Okay, going back to this problem, does that sort of help us at all? No, not really. Okay, I really need to be done with this. Mrs. Candy has a large box of lollipops, chocolate bars, and caramels. I personally find caramels to be gross. She wants to give each of the 9 children in her neighborhood 3 pieces of candy. Okay, so the 9 children in her neighborhood are all distinguishable. Once again, that's built into the fact that they're human beings. And so she's going to walk around, Mrs. Candy, not creepy at all, with a giant box of candy. How much candy does she have? She has every piece of candy in a quantity greater than 30. Ooh, why 30? Well, actually, why 27 would be sufficient? Because let's just say that there's one clear choice, like chocolate bar. If you walked up to me and said, you can have a lollipop, no, if you walked up to me and said, I have lollipops, chocolate bars, and caramels, I'm going to give you 3 pieces of candy. What do you want? My answer would be, give me 3 chocolate bars, because chocolate bars are better than lollipops and caramels. And so if everyone agrees that candy bars are the best, then one option is that every child can just have 3 candy bars. And so she better have at least 27 candy bars. Yeah, well, she's got more than 30 of every piece of candy. So she has enough, so she's not going to run out of candy. So, therefore, how many ways can Mrs. Candy distribute the candy? Well, that's kind of a little bit weird because now she's just deciding for every kid. Like, she's making up these gift bags in advance. She's not letting them have any choice in the matter. So Mrs. Candy is going to walk around to the 9 houses of the 9 children in her neighborhood and drop a little bag of candy at the foot of each person's door, and or whatever, in the mailbox or something. And instead of just doing it randomly or giving one kid 1 of each, maybe she's been doing this for years and she knows the personal preferences of the personal kids, and so she's putting time and effort and care into making this individual gift bag to this person based on their wants and needs and desires. How many ways are there to do this? Well, finally we now have a so-called stars and bars problem, because you should think of there as being lollipops, chocolate bars, and that's really annoying, Gossett, chocolate bars and caramels. And what Mrs. Candy is doing for each kid is choosing how many of those that she's going to get. And actually, you can almost just do like a raw count of this, right? She could give this person, of course, and then the candy is just being thrown loosely in a bag, so the order's all jumbled together. So all that matters is for each little gift bag, how many sort of ways can there be? How many different sort of bags are there, I guess? So you could give each person 1 of each, but you could also do sort of 2 lollipops and a chocolate bar, 2 lollipops and a caramel. 1 lollipop and 2 chocolate bars, 1 lollipop and 2 caramels, 3 caramels, 3 chocolate bars, 3 lollipops. All right, so actually you can pretty easily just go through them all, right? There's like one of each, that's one. There's the 3 lollipops, three chocolate bars, 3 caramels, so that's 4 now. And then I guess there's like 6 more where there's like 1 and 2. Yeah, because there are 3 choices of which there are to be 2 of, and then 2 choices of which there are to be 1 of. So therefore there are 6 ways. This is just a Fletcher problem over again. There are 6 sort of, even easier. There are 6 ways for the gift bag to be 2 and 1. Okay, so I claim that there are 10 ways for Mrs. Candy to produce a single bag of candy. But there's a more principled way to do this, I think now, and it's with the stars and bars approach. You have these bars. These 2 vertical bars are dividing the region of lollipops, candy bars, and chocolates. And now she has essentially $3 to spend on each kid, 3 stars. And so you put the stars, say, wherever you want, right? You let these 3 star characters float freely among these 2 bars. And this, for example, is a string. This string, star, star, bar, bar, star, is a string which indicates that this person's getting 2 lollipops and 1 caramel. And in fact, any string, so like say star, bar, star, that this string of stars and bars indicates that they're getting 1 of each. If the person's going to get all caramels, then that would be bar, star, etc. So you interpret 2. I think you guys get it. You interpret 2 consecutive bars to mean that having established this convention that we list them in this order, then the number of stars between the 2 bars, there are only 2 bars here, is the number of candy bars they get. The number of stars before the first bar is the number of lollipops they get, and the number of stars after the last bar is the number of caramels they get. Okay, I've just reduced this problem now to the problem of how many strings are there consisting of 2 bars and 3 stars. So if I have 2 bars and 3 stars, well, that's just a string of length 5. And 1, 2, 3, 4, 5. How many ways are there to make this string of length 5? Well, I'm just going to now put the stars wherever I want. So, and I have sort of some choices about where the stars go. And this is therefore just 5 choose 3. 5 choose 3 is the number of ways of choosing 3 objects from a set of 5 objects. Here the 5 objects are the 5 spots in the string, and the thing that I'm choosing 3 of them to be the spots that have stars in them. So, okay, of course 5 choose 3 is 5 times 4 divided by 2, which is 10. So that backs up the brute force method I was using earlier. There are 5 choose 3 ways of choosing which of the 5 characters of this string have stars in them. Alternatively, you could do 5 choose 2, because you could think of yourself as choosing which of the 5 spots have bars. But those are of course just the same. This is also 10. Okay, and for every one of these strings consisting of 2 bars and 3 stars, that's a unique way of distributing 3 candies. Okay. Therefore, there are 10 ways to do this for each kid. But then for each kid, she has an independent choice. And so really, you could say that this is just 5 choose 3 to the 9th. Because for each one of the 9 kids in the neighborhood, there are 5 choose 3 ways of choosing that for them. So the answer is just 10 to the 9th. So it's like 10 million or whatever that is. No, 10 billion. 10 something. 1 billion. Yeah, that's 1 billion. That's a lot of ways, Miss Candy. Okay, good. 2 problems left. How many odd 4-digit numbers can be created from the following digits? Assume that each digit can be used only once. Okay, I think this is like an easy problem, right? Because if the number is odd, then the final digit has to be odd. Well, only 1, 5, and 7 are odd. So I have 3 choices for what number goes here in the ones digit. But having chosen that number already, I have only 4 numbers left. So I have only 4 choices for which number goes in the first digit, and then 3 choices left for how many numbers go in the second digit, and 2 choices left for How many go here? So I guess the answer is 48 or something. No, so what happened? 9 times 4, 36, 72. Okay, there's one problem to return to. That's this problem 24. I'm sort of running out of effort level here, so maybe I'll just do this really fast. How many ways can you purchase 3 movies from a store that sells 57 distinct movies in unlimited quantities? Okay, the normal answer to this problem is, dude, if I'm going to walk into a video store, so this assumes we're purchasing movies, as in we're purchasing like a hard copy of a movie. So this already requires something that your generation doesn't understand, that you're going to like, buy like a DVD or something. So you walk into a store and you're going to buy a DVD. Well, there are 57 different movies for sale at this store. I want to buy 3 of them. Of course, I'm just going to grab the 3 and throw them into my bag. All that matters in the end is which 3 I bought. So the normal answer to this problem would be 57 choose 3. 57 movies. There are 57 choose 3 ways of picking which 3 movies I'm going to buy. However, note that Gossett says that these are available in unlimited quantities. That means that this is not some kind of weird used video store where there's only sort of like one of each movie, say. The movies are available in unlimited quantities. This, to me, indicates that, so I'm going to write, correct answer. The correct answer to this problem, if I'm on the same wavelength as Gossett, and I think I am, is that you might want to buy more than one of the same movie. Why would you do that? Why would you buy, Dr. Dolittle? Why would you buy sort of 3 copies of the same movie, say? Well, that would be sort of ridiculous. Well, but in the DVD era, you might want to buy, 3 copies of Dr. Dolittle. I'm referring to the 90s Eddie Murphy version of Dr. Dolittle, not the one from the 50s or whatever. And maybe you love that movie so much and you want to buy 1 copy for each of your 3 grandchildren, say. That comes up later. Okay, so we must allow for the possibility that we are actually going to buy one video more than once. Therefore, this is in fact a stars and bars problem, I claim. There are 57 different movies, and thus we have 56 bars separating those 57 movies. And you walk into the store with your 3 tokens, and if you're going to buy 3 movies, then you can place those tokens kind of anywhere you want, including the possibility that you might buy 2 copies of a movie. And if that's the case, then we have a string of length 59 consisting of 56 bars and 3 stars. And so I think that the correct answer to this problem is actually 59 choose 3. Okay, good. And then maybe I'm just not even going to touch this 24B. It's like it's even too weird for me. All right, good. That was like really fun. Apparently this Google thing only lets you go up to 20 frames. Well, I only need 20 frames because I'm going to do this last little thing now, and then this video will be over. This last little thing is something new. So this is a new thing, although it's like barely new because it's common sense, and it's even something that we did in Pre-Calc C, but we didn't do it in a formal kind of way. So imagine the following problem. Oh, I could have cut and pasted this, but I forgot. Here I'm just copying... I'm copying Gossett's example on page 229, in which we have 12 new cars. And here are the 12 new cars. What kind of cars are they? Just reading the problem out loud. A new car dealer has just received 12 new cars, all of the same model and with identical options. Okay, so they're exact same kind of, let's just say, for sake of argument, that they're the most beautiful car in the entire world, and that is the 2013 Mazda 3 hatchback. Okay, that's my car, and it's wonderful. Well, what do we have? We have 5 red cars. So we have red cars. We have 5. 4 are blue. 4 4 blue cars, and 3 are yellow. So yellow, 3. Okay. Question. The dealer wants to park them in a single row facing the main street. In how many visually distinguishable ways can the cars be arranged? How many ways can we line up the cars? So this is kind of an interesting problem, and yeah, if you have some shiny new cars, you want to park them right along the side of the road so people driving by see your beautiful set of 12 2013 Mazda 3 hatchbacks and think, man, I want to go to that car dealer and buy those. Also, you need to have a comically large American flag outside in front of your car dealership, and people will come and shop there and buy your cars. Well, these are all brand new cars. They're all exactly the same car. The only difference is the color. So built into this problem is the fact that you can't tell 2 brand new, identical red 2013 Mazda 3 hatchbacks apart from each other. So, so what? Well, how many ways, therefore, can we line the cars up? How many ways are there to put the cars in a row? Okay, and let's just do the problem now. Let's see. We have 12 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, I guess the first thing to do is just say, where should the red cars go? Well, I'm just going to throw some red cars into some places. How many choices do I have for how to do that? Well, I clearly have 12 choose 5 choices for which of my 12 spots along the side of the road will be filled with red cars. For every one of those choices of which 5 spots to fill with red cars, I now have, well, having filled 5 of the spots, 7 spots remain. And so I have to decide where to put the blue cars. And I could do maybe this. What are there, 4 blue cars? Yes, I'm done already. So I have 9 choose 4. What have I done? Not 9. Sorry. What did I say? 7 choose 4. I have 7 choose 4 ways of picking which of my 7 remaining spots will be filled with blue cars. For every one of my 12 choose 5 ways of picking which 12 spots will contain blue cars, I have, for every one of those, 7 choose 4 ways of picking which of the 7 remaining spots will be filled with red cars. And having done this, I'm now done. You can write 3 choose 3, but that's just being weird because now there will be 3 spots remaining and there are 3 yellow cars remaining, and so the choosing is done. Okay, that's how you would solve this problem if you were like a smart 7th grader, I think, or a smart pre-calc C student. But of course, you can look a little bit deeper at this, because what is 12 choose 5? Well, we've seen already, won't go through the logic again, that this is 12 factorial over 7 factorial 5 factorial. What's 7 choose 4? It's 7 factorial over 4 factorial 3 factorial. Okay, so this is pretty lame. This is called like learning by formula bashing or something. It seems that this simplifies into 12 factorial over 5 factorial 4 factorial 3 factorial. And now something is coming up, which actually happens a lot in this unit, which is by accident, my final answer got really simple, which indicates that there was perhaps a simpler way to do the problem in the first place. Was there a simpler way to think about this problem? Yes, there was. Instead, we could simply just answer this in sort of one step. And this is sort of clearly the answer. Why? Well, there are many ways of thinking about this. But one of them is to say, okay, there are 12 factorial ways. This is how I taught it in pre-calc C. There are 12 factorial ways to permute the 12 cars. But of course, that vastly overcounts the total number of distinguishable permutations, because the 5 blue cars, for example, are indistinguishable from each other. And so if any 2 blue cars were to swap places with each other, then that would be the same that would be the same distinguishable permutation, yet it would be a different permutation. So in fact, if you look really, really carefully, then the cars are distinguishable from each other. For example, they each have a different, vehicle identification number. So if you're willing to like crawl into the car and look at the dashboard and see what the VIN is, then of course you can tell the cars apart from each other. So really, there are 12 factorial ways of aligning the cars. But when you're just driving by the street, built into this problem, the understanding is that when you're just driving by the road, looking at the cars, you can't see the VIN. So any two blue cars are just blue cars. Therefore, 12 factorial is certainly the wrong answer to the problem. And in fact, it's a vast overestimate. How do I fix it? Well, I divide by 5 factorial because there are 5 factorial ways for the 5 blue cars to all swap places with each other. And therefore, the 5 blue cars in any particular distinguishable permutation, the 5 blue cars will be in 5 certain spots. But then there are 5 factorial ways that those blue cars could all switch spots, and you wouldn't even be able to tell. So to get the right answer, you need to divide by 5 factorial because you overcounted by a factor of 5 factorial. And similarly, you divide by 4 factorial because there are 4. Oh, I've been saying blue this whole time, but sorry, it's the red cars of which there are 5. Anyway, it doesn't matter. All right, this is how I taught this back in the day. In fact, there's even this like Mississippi problem, Mississippi. There's this Mississippi problem, which is how many distinguishable permutations are there of the letters in the word Mississippi, which I assign every year in Pre-Calc C. And okay, if you're a junior, maybe you got a very bad introduction to counting last year because I was like on paternity leave and stuff, and Esh taught this. I can't remember. But anyway, there are 11 characters in Mississippi, but there are certainly not 11 factorial strings you can make out of the characters in the word Mississippi because the 4 S's they're just S's. And so what we learned is that we needed to divide by 4 factorial, and also for the fact that the 4 S's can all swap places, and also divide by 4 factorial because the 4 I's can swap places, and also divide by 2. All right. This is a half-decent explanation, but I don't love it. And I think what we should really do is invent a new... anytime you find yourself doing division, you should not do division, and you should do multiplication, because it becomes more clear. So, all right, I hereby define a new symbol. Gossett calls it multinomial. He calls it multinomial. And then he just says like 5, 4, 3. And all right. I don't like that answer because it's just annoying to write out multinomial. Apparently it's standard, but not in our textbook, to write 12 and then you put like 5, 4, 3, and you put like a thing around it. So I claim right now, I define this symbol 12, 5, 4, 3, but I guess we can pronounce it multinomial 5, 4, 3 to be the number of ways to create a distinguishable permutation of 12 characters which appear in quantities 5, 4, and 3. So if I have 5 of one thing and 4 of another thing and 3 of another thing that are all indistinguishable from each other, then there are multinomial 5, 4, 3 ways of doing it. Okay, and now I'm going to prove as a theorem that this is the formula. How? Via multiplication. If this is the number of distinguishable permutations, then let me multiply by 5 factorial, and let's just stick to the cars, right? If there are this many ways, if this is just the answer to our problem, and then we reason indirectly, then there are 5 factorial ways for me to permute the 5 red cars amongst each other. And for every one of the ways of doing this, there are 5 factorial ways to do that. And for every one of the ways of doing that, there are 4 factorial ways to put the 4 blue cars in order amongst themselves. And there are 3 factorial ways to put the 3 yellow cars in order amongst themselves. Well, if you first create all the distinguishable permutations of the 12 cars, and then you permute the 5 cars, the 5 red cars in the correct in some kind of order amongst themselves, and then you permute the 4 blue cars amongst themselves, and then the 3 yellow cars amongst themselves, you have in fact just permuted all the cars. And so the answer to this is just 12 factorial. In other words, I have this equation. Both sides of this equation counts the number of permutations of the 12 cars. Another way to think about this is, suppose that the cars are indistinguishable. Suppose there are 5 red cars, there are 4 blue cars, and there are 3 yellow cars, but this is some hippie car company in which, the cars all get tie-dyed with red, but in some kind of, they're like artisanal cars or something. And so no 2 red cars from this Mazda company are unique. And so every red car, in fact, you buy a car that's red, but really every one is different slightly because it has a different red tie-dye pattern. Well then, then there really are 12 factorial ways to order the 12 cars in a visually different pattern. Alternatively, we could answer this problem by counting how many ways, only now caring about the color, there are multinomial 5, 4, 3 ways of deciding the visual layout of the cars only with respect to what their primary color is, red, blue, or yellow. But then, having chosen the sort of red, blue, yellow pattern, there are then 5 factorial ways for me to scramble now the 5 red cars, which all now look slightly different from each other. 4 factorial ways to scramble the 4 blue cars, because they all look slightly different, and 3 factorial ways to scramble the 3 yellow cars. And so, what I'm doing now is I'm claiming that these are 2 different ways of solving the same problem. And therefore, these are the same formula. And therefore, I've now proven to you that 12, 5, 4, 3 is equal to 12 factorial over 5 factorial, 4 factorial, 3 factorial, because by just doing a simple division. So this is how you prove a combinatorial formula, I think, from sort of more low-level principles. All right, this video is twice as long as it needed to be, so I hope you watch it on 3 times speed. Goodbye, everybody. Oh, so then you have a whole bunch of homework problems, which are all I think much harder. So if you've never done any math team, you're going to find every problem from the next section to be basically more difficult than any problem we did in Pre-Calc C. So this is going to be a great learning experience for you, and you're going to have it all done by Friday. Woo! For our half day. Can't wait. All right, goodbye, everyone.